So in this video, you are going to learn Maxwell's equations. So Maxwell's equations are the universal laws, just like the law of gravity. So these are the equations which govern the relationship between electric and magnetic fields. As the signal propagates through space, it propagates in the form of electromagnetic wave. So the electric field and the magnetic field, it propagates together. It is necessary to know how the electric fields and the magnetic fields they propagate and how they vary together. A flow of electric current will produce a magnetic field. If the current flow varies with time, which happens in case of periodic signal, the magnetic field will also give rise to an electric field. Maxwell's equations shows that a separated charge gives rise to an electric field. And if this is time varying in time also, it will give rise to a propagating electric field, which further gives rise to propagating magnetic field. So these are what are the Maxwell's equations. So let us proceed to find out more details about this Maxwell's equations. So there are four Maxwell's equations, and each of these Maxwell equations has two forms, the integral form and the point form or differential form. So first we'll discuss about the Maxwell's equations for static fields. Then we'll see the Maxwell's equations for time varying fields. So in case of earlier chapters, we have studied electrostatics and magnetostatics. That is Gauss law, Ampere circuit law, and so on. So from these different laws, we have already written some of the equations. So let us list out the Maxwell's equations out of this. So first, let us discuss about the Maxwell's equations for static fields. So from Faraday's law, the work done over a closed path or closed contour is always zero. That is, the line integral of electric field over a closed contour, it is equal to 0. Now using Stokes' theorem, the closed line integral from this equation can be converted to a surface integral. So converting to surface integral, line integral E dot dl, this becomes surface integral curl of E dot ds. Now this is a dot product of curl of E and ds. Now ds, it is a small differential area which is non-zero quantity. So if ds is not 0, then to satisfy this equation, we must have curl of E equal to 0. So we can conclude that curl of E, it must be 0. So this is the first Maxwell equation derived from Faraday's law, and this is called as the point form or differential form of Maxwell's equation derived from Faraday's law for static fields. So this is the integral form of this equation, and this equation what we have written, del cross E equal to 0, it is the point form or differential form. Now let us go to the next equation. The next equation, it is derived from Ampere's circuital law. So Ampere's circuital law says the line integral of a magnetic field intensity H around a closed path is exactly equal to the direct current enclosed by that path. So mathematically this is line integral H dot dl is equal to I. Now the current I, the term on the right hand side, this can also be written in terms of current density. So current I in terms of current density, it is over the surface integral J dot ds. So taking surface integral of J dot ds, that gives us the current. So substituting this here, we can write this equation as integral H dot dl equal to I, or that is equal to surface integral J dot ds. So this is the next Maxwell's equation derived from Ampere's circuit law. So this is in integral form. Now let us find out the point form or the differential form of this equation. So applying Stokes' theorem on the left hand side, so the line integral H dot dl, which we can express as surface integral of curl of H dot ds, which is equal to surface integral J dot ds. Now if we compare left hand side and the right hand side of this equation, we can write del cross H is equal to J, that is the current density. So this is the point form of Maxwell's equation derived from Ampere's circuit law. Next one, it is derived from Gauss law. So as per Gauss law, we have seen the electric flux passing through any closed surface is equal to the total charge enclosed by that surface. So mathematically this is the electric flux psi is equal to the surface integral d dot ds, where d is the electric flux density and which is equal to the charge enclosed. So this is the statement of Gauss law. Now we have seen earlier that the charge enclosed over the given volume, it is nothing but integral rho v dv, where rho v, it is the volume charge density. So this becomes the next Maxwell equation, that is surface integral d dot ds is equal to volume integral rho v dv. The Maxwell's equation derived from Gauss law for static electric field. So this equation, it is in integral form. Now we can represent the same equation in point form or differential form. So applying divergence theorem, the left hand side, that is the surface integral, we can represent it in terms of volume integral. So surface integral d dot ds, it becomes volume integral divergence of d dv. So substituting this on the left hand side, and if we compare these two equations, we can easily say that divergence of d, that is del dot d, it is equal to rho v. So comparing these equations, divergence of d is equal to rho v, that is the volume charge density. So this is the point form of this Maxwell's equation. The next one is the last Maxwell's equations, equation number 4. It is derived from Gauss law for magnetostatics, which says that the magnetic flux cannot reside in a closed surface due to the non-existence of single magnetic pole. So if we have a magnet, north pole, south pole, the magnetic flux, it will always exist in the form of loops. We cannot separate a single pole from this magnet. A single magnetic pole does not exist. So this means if we have some closed surface and inside this closed surface there is a magnetic field, then in that case we have discussed the magnetic field, it always exists in the form of loops. So this means whatever flux is entering inside this closed surface, the same amount of flux is leaving outside of this closed surface. So mathematically we write it as surface integral B dot ds is equal to 0. So this is the Maxwell equation derived from Gauss law for magnetostatic field, and this is the integral form. So let us find out the differential form or the point form of this equation. So for this purpose we apply divergence theorem here. So the surface integral B dot ds, we can write it as volume integral divergence of B dV equal to 0. Now dV, it is a small volume which is a non-zero quantity. So that means divergence of B, it must be 0. So this is the point form or the differential form of Maxwell's equation derived from Gauss law for magnetostatic field. So these are the 4 sets of equations for static fields. Now let us find out the Maxwell's equations for time varying fields. So the Maxwell's equations for time varying fields, these are modifications, these are extensions of the Maxwell equations for static fields. So let us start from the same 4 equations again. So the first equation, as we have seen earlier, from Faraday's law we can say surface integral E dot dl. Now in case of static magnetic field, the surface integral E dot dl, it was equal to 0 in case of static fields. So this was the Maxwell equation in static field. But in case of time varying fields, this is not 0. So this is EMF induced actually. So this is a negative integral surface integral dB by dt dot ds. This means the total electromotive force or the EMF induced in a closed path is equal to the negative surface integral of the rate of change of flux density with respect to time over an entire surface bounded by the same closed path. So this is what is represented by this mathematical equations, which is applicable for time varying fields. Now converting the line integral on the left hand side to surface integral. So E dot dl we can express as curl of E dot ds. Now in this equation both sides are surface integrals. So this means we can write this as del cross E is equal to dB by dt. So this is the Maxwell equation in point form for time varying fields. So this is the integral form derived from Faraday's law, and this is point form or the differential form. Now we have seen earlier in case of static fields, this is del cross E is equal to 0. This was the Maxwell equation for static fields. For time varying fields, it is non-zero. So that is negative rate of change of magnetic flux density. So this is the Maxwell equation derived from Faraday's law in case of time varying field. Now the next equation which is derived from Ampere's circuit law. As we have seen, H dot dl, line integral of magnetic flux density over the given closed path, it is equal to the current enclosed by that closed path. Now replacing the current by surface integral, this equation we write as surface integral J dot ds. We have seen earlier, in case of time varying fields, the current density J, it has two parts, the conduction current density and the displacement current density. So substituting for this J as J plus dd by dt, where this is the conduction current density. Now displacement current density we have seen in one of the videos, it is equal to rate of change of electric flux density. Substituting this here, this is the Maxwell's equations derived from Ampere's circuit law in integral form for time varying fields. This is also called as mesh equation or the mesh relation. Now to find out the point form, we apply Stokes theorem. So the left hand side H dot dl, line integral, we can represent in the form of surface integral as del dot H dot ds. Now again, if we equate LHS and RHS, then we can say del cross H is equal to J plus dd by dt. So we can write this as del cross H, that is the curl of H, is equal to conduction current density plus displacement current density. So this is the point form of the Maxwell's equation for time varying field derived from Ampere's circuit law. The third equation, which we have derived earlier, in case of static fields, it is integral d dot ds is equal to the charge enclosed. Now the charge enclosed we have seen, it is same as the volume integral rho v dv. So this is the Maxwell equation in integral form in case of time varying fields. Now this equation remains similar to the Maxwell equation what we have seen for in case of static fields. Now similar to what we have seen earlier, the left hand side we can represent in terms of volume integral by using divergence theorem. So left hand side surface integral we convert into volume integral using divergence theorem. So volume integral del dot d dv equal to volume integral rho v dv. Now from this equation, if we compare left hand side and the right hand side, then we can write del dot d is equal to rho v. This becomes the point form of Maxwell's equations. So this is same as static field. So del dot d equal to rho v, that is the volume charge density. Now the last equation, which is derived from Gauss law for magnetic fields. So we have seen earlier, the single pole cannot exist in case of magnetic fields. What we have seen earlier in case of Maxwell equations for static fields. So that is surface integral b dot ds is equal to 0. So this means whatever flux is entering inside the volume, same flux, it will leave this volume. Because of this, we can say the surface integral b dot ds is equal to 0. So this is the Maxwell's equations, which is derived from Gauss law for magnetic fields, which is in integral form. Now, using divergence theorem, the surface integral, we can represent this in terms of volume integral as volume integral del dot b dot dv equal to 0. Again, we know dv is small differential volume which is not equal to 0. So because of that we can write divergence of B is equal to 0. So this is the point form of the Maxwell equation derived from Gauss law for magnetic fields. So this is the integral form. This is point form or differential form. So these are the four Maxwell's equations for time varying fields. Now let us list out all the equations together. So all these four equations derived from Faraday's law, Ampere's circuital law, Gauss law and Gauss law for magnetic fields we have listed here. This is for time varying fields. So the first equation, curl of E equal to minus dB by dt. In case of static field, this becomes 0. Now in the same manner, the integral form of this equation, we can say this is equation number 1. Integral, line integral E dot dl equal to negative surface integral dB by dt dot ds. Now again, in case of static fields, rate of change of flux density, it will be 0. In case of static fields, the magnetic flux density, it will be uniform. So rate of change of flux density, it will be 0. So this can be written as 0 for static fields. Now in second equation, del cross H is equal to conduction current density plus displacement current density. Now in case of static fields, this second term, this is equal to 0 for static fields. Similarly, this is the integral form. So here also the second term, it will be 0 for static fields. So this is the equation number 2, point form and the integral form, which is derived from Ampere's circuital law. Now equation number 3, divergence of D is equal to rho V. So this equation, it remains same in case of static as well as time varying fields. So this is the integral form, surface integral d dot ds, which is equal to volume integral rho v dv. Now the equation number 4, which is derived from Gauss law for magnetostatics. So that is divergence of B is equal to 0, the point form, and the surface integral B dot ds is equal to 0, which is the integral form. Again, in this case also, in case of static fields, it remains same. So these are the 4 Maxwell's equations for time varying fields as well as for static fields. These are the Maxwell's equations which are in general applicable anywhere. Now for specific applications, these equations can be modified by applying the particular conditions. So if we consider example of free space, now for free space, there are no sources. So in that case, the current density will be 0 as well as volume charge density, it will be 0 in case of free space. So accordingly, these equations are modified here. So the first equation, it remains same, and second equation, in case of free space, the current density will be 0. So here J is equal to 0. So that's why instead of J plus del D by del T, this is simply dd by dt here. So in the same manner, here also J is equal to 0. Now similarly, for equation number 3, we have seen, so in case of free space, this rho v will be 0. Volume charge density, it will be 0. So here, in case of free space, rho v is equal to 0. Here also, rho v is equal to 0. Last equation, it remains same for free space. This is how the Maxwell's equations can be applied for different applications. For example, in this case, if you want to find out how the electromagnetic wave propagates in free space, in that case, this four set of equations can be used to find out the corresponding electric fields and magnetic fields. So this is how the Maxwell's equations can be used. Now later on, in further topics like uniform plane wave propagation, we will make use of these equations to find out the expressions for time varying electric fields and time varying magnetic fields.